Welcome to the Derive the Five lesson. In grade 11, I gave you these five, we call them the Big Five. One, two, three, four, five formulas for solving kinematic problems with constant acceleration. What we are doing in this lesson is we are deriving them. We're going to prove them. Maybe you trusted me enough last year that they are true, so we're going to actually show and prove that they are true. And so for this page and the second page, these two pages, we'll fill out some notes and we'll do a form of proof of showing that they're true. And then notice what your homework is going to be. Homework is going to be practicing Derive the Five on the next page. So the next page, it's mostly blank, but it's got a little bit of there. And then you will get a surprise quiz that will look exactly like the next page. In fact, it's the same page. I'll just photocopy it for you. And the question will be derive the five. You're going to get 2 marks for each of the 5, so it's a total of 10 points. Some of them are a bit easier, a couple of them are a little bit harder, to get 10 out of 10 on it. So essentially, if you can, well, I guess the one strategy would be have a photographic memory and just write down every little notation. But actually, if you understand it, it isn't really that hard to figure out how to derive these 5. So the things that you start off with, you get this generic VT graph. Okay, so this is the velocity side, this is the time side. This has VO in it. I like to say V1 and V2, so I'm just going to scribble this out and say V1 here, and then here I'll put V2 like that. But it does have T1 and T2. And so you'll notice one thing about this is that the difference between V1 and V2, so it'd be like this one here, will be delta V. So that's the change in V. The change in something is always the second one minus the first one. So this, in other words, if this is the first point and this is the second point, right? This will be the rise part and this will be the run part of that triangle. All right, so let's start off and we're going to start looking at the first, notice in the first 3 equations that they all are solving for delta D. And so on a VT graph, our previous lesson was just saying that delta D is the area under the VT line. So what we're going to do is we're going to find 3 different ways to figure out the area under the VT line. And a reminder, that area would be, if I color it right now, it would be this kind of area here, like this. See if I can get it nicely done. So really what we need to do is 3 different ways to find the area. This feels a little bit like kindergarten here, to get that yellow space. Okay, so the first one that I think jumps out at you right away is to say it is a rectangle plus a triangle, right? So this would be the rectangle and that would be the triangle. So just as a reminder of how to do that, so this would be the rectangle, right? And then this up here part would be the triangle on the top, right? So this area plus that area. So equation number 1, delta D is the area under the VT line. So if you were, given the question and you were, where we go? Let's say that this was your way scrolling way down here. You could say number 1, right? Area, or delta D equals area under the VT line, right? So I am actually giving you a little bit of this stuff so I don't have to write it out every time. But this would be included things that you would be expected to write. Area under the VT line. And one way to figure out that area is a rectangle plus a triangle. The area of the rectangle is going to be length times width, and the area of the triangle is going to be base times height over 2. Now that length, let's consider what that length is. The length of this here, this is delta T. From here to here is delta T, and the height is V1. So this rectangle is V1 times delta T plus, now the base times height divided by 2. I'm going to bring out this half part out front. Okay, so that's the divided by 2. It's the same thing as saying a half multiplied by the base. Now that base is still the delta T, and the height is, this height is delta V. You know what, I'm just going to switch that area around. No, I'll just leave it like that. So we're almost there. You are given these 5. So you can look at this, you can say delta D is V1 times delta T plus 1/2 A delta T squared. It looks pretty close except for this part isn't quite the same. Alright, this is the part where you're going to bring in and you're going to think, okay, acceleration, and this is also here, the definition of acceleration is delta V over delta T. So if I take that and I solve for delta V by multiplying both sides by delta T, I'll get A times delta T. And that's what I'm going to do. I'm going to substitute. Okay, so substitute that delta V is equal to A delta T. So rewriting the next line, I'll get delta D is equal to V1 delta T plus 1/2 delta T times, now instead of delta V, I'm going to have A delta T. See how that works. And my last line, I didn't quite have enough space, so I'll write it beside. Delta D is equal to V1 times delta T plus 1/2 A delta T squared, because I've got a delta T here and a delta T there. And we've done it, okay? We've solved the first one. What have we used? We've used a generic VT graph, and we've used this idea that the area under a VT line is delta D. So there is equation number 1. I just want you to notice a little bit something. If the velocity was constant, then that would be, the line would look like this, right? And this block here would represent how far someone went, or the object went, if they were going at a constant velocity. But because in here that the object is accelerating, the triangle represents the extra amount that the person would have moved, or the object would have moved, because of the acceleration. So looking over here, this is the rectangle, this is the triangle part. This is how far, if this V1 was the same throughout, if it was a constant velocity, that's how far they would have moved because of that. And it looks a lot like our, delta D is equal to V times delta T. But since they're accelerating, there's going to be this additional part, and that's the 1/2 A delta T squared. Okay, so let's look at the second one. And again, now you'll see the difference. We still start off exactly the same, but now it's the area of a big rectangle minus the triangle. So the big rectangle, since I put that word big in red, the big rectangle would be this kind of big rectangle that I'm outlining in red here. Okay, so it would be the big rectangle. Okay, subtract. Now the triangle part that we're going to subtract would be this triangle here. Okay, so instead of adding, we're going to be subtracting this one up here. Okay, the area of the big rectangle, the base is still delta T, but now the height, instead of it being V1, the height is V2. So here I'm going to say delta D is equal to V2 times delta T minus, now that area of this triangle, it still has the same base as my one from question 1, and it has the same height. So although it's in a different position, it is actually the identical area. So I can use that same 1/2 delta T times delta V. And again, I can do that same substitution. I won't write it all out as much. I'll write delta D is equal to V2 times delta T minus 1/2. And now I'll write delta T, and then parentheses I'll write A delta T. So I didn't write the word substitute, and I didn't write this stuff off to the side this time because I've already done it once. So my final line is delta D is equal to V2 times delta T minus 1/2 A delta T squared. And I've done it. Okay, so I've done 2 out of 5 already. I've gotten 4 marks out of 10. Now in the first example, this was how far the object would have moved had it gone at a the constant velocity to begin with. Now if you think of, and the same idea as if it started from a slower velocity and ended at a higher velocity according to this graph, if it would have been going at that higher final velocity the whole time, it would have gone farther than it really did. And so we have to subtract some area here because it wouldn't have gone as far because it started from slower, if that kind of makes sense to you. So this term here, v2 delta t, would be how far it would have gone, the delta d would have been, had it been going at its final velocity the entire time. But since it had to speed up to get there, oh, and I forgot a squared here. Since it had to speed up to get to that speed, we have to take away that part. Okay, so this last one, again, it's a delta d is equal to the area, but now it's going to be the area of a trapezoid, or another way to think of it, or average velocity. Okay, so I'll do both of these. So first of all, if you're familiar with what a trapezoid is, and did I give you a formula of a trapezoid up here? Yeah, here you go. So thinking about the area of a trapezoid, so a trapezoid has two bases. So I'm going to put here's base 1, and has a higher base up here, base 2. And so what is a trapezoid? A trapezoid has two parallel sides, so the bases are parallel. And then there's going to be some height between it. So I'll draw, this will be, say, my height. The height is that perpendicular one. So if you see that the area is the average of the bases, b1 plus b2 over 2, multiplied by the height. Okay, so what's different here is that if you can see, I'll do a little bit of erasing. There we go. So the trapezoid here, it's kind of, we have to sort of rotate it 90 degrees. So this is one of the bases here. Oh, this would be one of the bases here. Get a nice big line here. Okay, here's one of the bases in blue. There we go. So that's B1. And then here is the other base here, B2. And then this section here would be my height. Okay, so if you imagine this thing here and you rotate it, so here's one base and here's the other base, and then there's the height. So if you consider that way, the area of the trapezoid, it becomes very simple right away. So we say the area, delta d, is equal to b1 plus b2 over 2 multiplied by the height. And let's consider, what is base 1? Well, base 1 is v2, the final velocity. Base 2 is the initial velocity. So it's going to be v2 plus v1 all over 2 multiplied by the height, and the height is this line here, which is delta t, right? So that's delta t. And then all we got to do really to make this right is to make it look exactly like the formula. We'll say delta d is equal to v1 plus v2 divided by 2 all times the t, right? If you think of it as average velocity, so again, I'll do a little bit of erasing here. So if yeah, sure, if we get rid of all this stuff. If we think of it as average velocity, so the average velocity, even though it starts from v1 and ends at v2, if we consider this halfway point here, right, this would be equivalent to having a constant velocity halfway in between. Right? So this spot here would be halfway in between those two values, which would be v1 plus v2 over 2. That's what the halfway point would be, the average of those two numbers. So this area would be equivalent, because this triangle and that triangle are the same, would be the same thing as using our average velocity idea to say delta d is equal to v times delta t, where this is the average velocity. So don't do this very often, but you can also think of it as an average velocity. So if v av is equal to delta d over delta t, that means that delta d is equal to the average velocity times delta t. So delta d is equal to v1 plus v2 divided by 2 times delta t. So you can say either. These are both good methods. Either way, we'll get you 2 out of 2. All right. Equation number 4, it says start with the definition of acceleration and then solve for v2. And I rewrote this stuff here, so we're going to start with the definition here. So this is not a graphical one, this is more like a algebraic one. So I'm going to start with a is equal to delta v over delta t. And it helps to see what is equation number 4. We've got to make it look like that. All right, so I guess 2 things need to happen. First of all, we need to break delta v up into v2 minus v1. And then the second thing we need to do is solve for v2. So think about all the things that are happening. The first thing we should do is multiply both sides by delta t. And then we should add v1 to both sides. So we get v1 plus a delta t equals v2. And then maybe just switch the order so that it looks right. v2 is equal to v1 plus a delta t. And when you think of it, this one makes a lot of sense, doesn't it? The final velocity is going to be equal to the initial velocity plus, well, this is the change in the velocity, right? This is how much, if it's changing by 2 meters per second every second, multiplied by how many seconds, right? So this kind of makes sense that this term here is our change in velocity. So it's going to be v2 equals v1 plus a delta t. The last one is a toughie. Okay, so again, it's an algebraical one. So we're on equation number 5, and I'm thinking, hint, 5 is equal to 4 plus 1. So if this is equation number 5, we're going to use equation number 4, and then later on we're going to use equation number 1. Looking at equation number 5, there is a lot of similarity between 5 and 4. 5, on the left-hand side, it's solved for v2 squared, and equation 4 is v2. So what we're going to do is we're going to start with equation 4. Okay, start with equation number 4. So that is, and we just solved it. So it's right there, v2 is equal to v1 plus a delta t. Now, in order for us to make it look like this, we're going to square both sides. So we'll square this side, and we'll square this side. Now, careful, you algebraic people out there. The left-hand side is easy, v2 all squared. Now this one, remember when you square a binomial, a plus b all squared, another way to think of it is to think of it as a plus b times a plus b. And then if you use FOIL, you get a squared, that's the first, and then the outer, a times b, and then the inner, which is another a times b, and then the last is b squared. So you get a squared plus 2ab plus b squared. So some of you remember that this is the pattern. Later on we just go when we say okay, so remember that this ends up looking like that. Okay, so we kind of remember that pattern. It's the first one squared plus 2 times these two multiplied together times the last one squared. So let's follow that. v1 squared plus 2 times these two multiplied together. And now I got 3 letters, so I don't know, let's kind of go alphabetical. Let's do the A, and then the V1, and then the delta T. Okay, so I've got, I know it's crazy, 3 letters there, plus the last one squared. Now be careful. A times delta T, like this, A times delta T squared is going to be equal to a squared delta t squared. You'd be amazed, here I'm going to just do more erasing here just for keep things clear. You'd be amazed at how often people forget this squared right there. Okay, because they're used to writing from equation, the first two, 1/2 a delta t squared, but it's a squared delta t squared. Well, now let's take a gander over here. We're pretty close, right? v2 squared equals v1. Now we got a v1 squared. This part here, well, our work now is to take this part here and make it look more like that. So do you see, and also remember we're going to be using equation number 1. Okay, so let's just go back. What's equation number 1? Delta d is v1 delta t plus 1/2 a delta t squared. Okay, so here's the key. and I'll write you a note here. Please factor out 2a from the last two terms. What does that look like? Well, okay, v2 squared is equal to v1 squared plus, so I'll factor out a 2a. So from this term, when I factor out the 2a, it's really dividing that 2a, so I end up with a v1 delta t. When I factor it out of here, some of you might say, Mr. Spadley, there's no 2. How can I do that? So if, there's a 1 there now. If I factor out the 2, it's like dividing out a 2. So I'm going to get a 1/2. And then when I factor out the a part, instead of a squared, I'll just have a. Okay, now check it out. v1 delta t plus 1/2 a delta t squared. That is so cool because that is this. Okay, that is exactly that part. So now we're going to substitute. Maybe I'll write a little line in between. I've been doing stuff in blue, but substitute delta d is equal to v1 delta t plus 1/2 a delta t squared. So because it's equation number 1. So our next line will be v2 squared is equal to v1 squared plus 2a, you got it, delta d. And we are all done. That one is a very hard one to visualize, to understand, but it gets the job done. And there is more than one way to do it. This is my favorite way. It's a little bit hard algebraically, so you got to maybe practice this one a little bit. So here's what I've done for you. What you should do is take this sheet and see how much you can do all on your own, and as many times you have to peek, but this is what your quiz is going to look like. I'm going to hand this sheet to you, and basically if you can recopy every line from here, or at least have some kind of argument or mathematical argument that I can understand that comes to the exact same conclusions, then you'll do it well. So good luck, and I will see you in class.